Why are photonic qubits good for room temperature quantum computers? Imagine a world where quantum computers can run without giant cooling machines. That's where photonic qubits come into play, using particles of light to do the heavy lifting. Photonic qubits use photons, the tiny particles that make up light, to carry and process quantum information. Unlike other types of qubits, photons don't need super cold temperatures to stay in their quantum states. This is a big plus because maintaining extremely low temperatures requires complex and costly cooling systems. Photons naturally resist decoherence, which is when quantum information gets lost because of environmental disturbances. They don't interact strongly with their surroundings, so they keep their quantum properties at room temperature. Superconducting qubits and ion trap qubits usually need to be cooled close to absolute zero to prevent losing information, but photons don't have this requirement. Another advantage is that photons are already used in fiber optic networks for long-distance communication. This means photonic qubits can easily integrate with existing optical infrastructure. This compatibility opens doors to scalable quantum networks and even the idea of a quantum internet. Photonic qubits also allow for quick quantum operations. Since photons travel at the speed of light, they can be manipulated rapidly with simple optical tools like beam splitters, phase shifters, and waveplates. These tools help perform quantum gates faster, which is essential for practical quantum computing. Recent progress has shown that error correction techniques can be applied directly to individual photonic qubits. This simplifies hardware design and makes it easier to build larger, more reliable quantum systems that work at room temperature. Of course, challenges remain. Controlling and entangling photons precisely is tricky, and some photon detection methods still need cooling. Plus, photon loss during transmission can be an issue, but ongoing research is improving detectors and transmission methods. Despite these hurdles, photonic qubits hold great promise for creating quantum computers that don't need bulky cooling systems. They could make quantum technology more accessible, affordable, and easier to use outside specialized labs. In short, photonic qubits are ideal for room temperature quantum computers because they keep their quantum states without needing cold temperatures, work well with existing optical tech, support fast operations, and can be scaled up more easily. This makes them a strong candidate for the future of practical quantum computing.